Hello, my name is Alexandru Calotoiu, and I will talk about how we can obtain better performance from C code with the help of Dataflow optimization. First, a bit of motivation. For the foreseeable future, data movement dominates energy costs. Whatever architecture is considered, the further we must move data, the more expensive it is. Therefore, making sure that data movement is optimized is paramount to energy efficiency and ultimately for performance. However, efficient data movement is hard. There is a lot of research in how to do this, and while everyone agrees it is an important topic, it is by no means solved. Now, I will focus in this talk and in this work on C, and classifying research in this area, we can identify that there are multiple larger categories of research. I would say we have IRs, which are frameworks that generate code for multiple platforms, helping with performance portability, compiler that use polyhedral analysis to uncover parallelism opportunities and make better use of current parallel architectures, and many general compilers which try to optimize for the available hardware and even auto-parallelize in the case of ICC. What makes all of this so hard? Pointers and aliasing, indirect accesses, and of course, whole program analysis is expensive and difficult. All of these are obstacles in the way of understanding code and improving code. And we, in this work, will try and use a different framework to optimize and improve the performance of C codes. We wish to use data-centric parallel programming, a framework which has been developed in our lab. It is a framework that, similar to LLVM, generates efficient code for multiple architectures by relying on the SDFG IR, which stands for Stateful Data Flow Multigraphs, an IR focused on understanding data movement. Now, would it be possible to lift C into this IR and benefit from its optimization opportunities? I'm going to explain why this would be beneficial in a second, but first, let's talk a bit about the SDFG IR. Let's start with a very simple example, starting from a line of code in a stencil. This would be a Jacobi one-dimensional stencil. We want to separate the actual computation, the tasklet, from the data containers and be able to represent and analyze which data elements take part in the computation. So these are the data containers, and we want to know exactly which parts of these data containers, so which memory regions are accessed, for which we use memlets. Now, this is the core of the idea, but this we can also represent more complicated constructs such as control flow, such as a loop using a state machine. So in this case, we would encapsulate this computation, this tasklet with its memlets in a state. And then for something like a for loop, we represent a state machine. An important aspect here is that state transitions and memlets are analyzed using symbolic expression, which is DACE uses a powerful symbolic analysis engine. It will become important later and allows, in short, detailed analysis of data access patterns. Now that we had a short crash course in what an SDFG is, let's move on to the question of why translate C to DACE? Well, as discussed in the previous slide, if we could bring C code, such as a Jacobi 1D stencil, into DACE, then we could generate GPU code, FPGA code, and improve data movement with transformations such as tiling and reordering of loops simply automatically. From there, the next step would be to perhaps add auto-parallelization to the code by leveraging our capability of understanding data access patterns. For example, in this case, adding pragma parallel for loops. Now, this is a very simple example. So for the next, and for showing how to lift code from C to days, and let's try a more complicated example. Sparse matrix vector product. So the way that we do this is by starting with AST transformation. So we take the code, we generate the AST, and then we prepare the AST for transformation into an SDFG. We do this by first making some simple transformations, making basic block explicit, some transformations which are more involved, such as extracting all array indices, which leads to effectively an SSA form, so static single assignment form for all array access patterns. This will be important later, and many other such transformations. The main goal here is to canonicalize the program representation and allow our translation to the SDFG to make simplifying assumptions. Now, a problem which most C compilers have is one that indirect accesses are very difficult to analyze and are a significant obstacle in optimization. This is why we have extracted these array indices, because the assumption of having them in an SSA form allows us to later make simplifications and improvements to this. Now, going forward, we now translate the C code to an SDFG using similar constructs. So the assignments computations become tasklets and everything else becomes a state transition. This is now the transformation of this code. Now, notice in this example that we still don't know where X is addressed. This is an issue. And even though the SDFG representation at this point generates valid results, it is a direct representation of the control flow centric C code and will not offer us any performance improvements. Also, it cannot be optimized directly with the tools DAYS has available, so we work towards expanding this tool set. Again, the first thing that we have to figure out is how to handle that indirect access. What we do in this case, we introduce the concept of symbolic scalar analysis, which involves us improving the understanding of data access patterns by allowing symbolic manipulation of such data access patterns. To do this, we introduce this transformation called symbolic scalar analysis, and we transform the index access to X, to the array X in this example, from data access to a symbolic access, allowing our symbolic access, analysis engine to play with it. This fixes the issue of indirect accesses not being analyzable. The transform code would look like this then. And now it allows us to reason about how X is accessed. A further improvement and transformation that we add is update detection. This allows us to more effectively parallelize the code by creating an update type of assignment, supporting config resolutions for multiple operations. With these transformations, we can now proceed to the final step, which is auto-parallelization, transforming the code from this serial version to one where we have expressed the parallelism of the code in a parallel scope, and then this can be made, for example, on a CPU into OMP parallel for loops, or on a GPU into a kernel, or CUDA, and so on. So to summarize, we have now discussed a way to bring a C code, a small piece of C code, into SDFG IR kernel, and how then to auto-parallelize it. Trying out different compilers, including polyhedral compilers, DACE and ICC parallel were able to parallelize this very small kernel. Poly and Pluto were not, and Pluto even crashed when we tried. Now, so far, I have only discussed very small kernels. However, one of the issues, one of the barriers in optimization is the fact that whole program analysis is difficult and expensive. And we introduce in DACE a transformation called access pattern propagation, which has the benefit of allowing us to improve performance in the analysis and transformation of a program representation. Part of the benefit of DACE is the capability of understanding and analyzing data access patterns. Now, this means that whenever we have some part of the code, we want to know what is being accessed in a read fashion, in a write fashion, which parts of the data containers are being used. However, as this happens on different levels of a program, as we zoom out, so to speak, we would like to know in each concept, in each level of zoom, in each scope, what are the accesses there. We introduce a recursive way of propagating this information across all levels of the intermediate representation, which allows us, when trying to discern whether or not two functions, two loops, two statements can happen in parallel or have data dependencies from one another, to ignore everything that happens on the levels below them. This means that as we zoom out increasingly and try to find out what the data access patterns are, we only need concern ourselves with the current level, and the levels beneath them are no longer important. This makes the process of whole program analysis much more efficient and allows us to perform more powerful passes. A last engineering contribution that we provide in our work is how to order dataless dependencies. So if we have functions which are outside the scope of our analysis, opaque functions, system functions such as random, a problem is that with no explicit data flow dependencies, our IR would be able to reorder such accesses. In this case, if we know that external libraries can have an internal state, we simply add auxiliary data flow, the dummy data flow variable, to ensure that the order is preserved. To evaluate our work, we have first looked at bolibench, a set of 30 benchmarks, which have been originally developed to test polyhedral compilers. These are very small kernels, and we have compared against many state-of-the-art compilers and auto-parallelizing compiler tools. Our approach itself only relies on discerning data access patterns and ensuring that there are no data races. We are not leveraging polyhedral analysis in our approach yet. However, we do look at the entire program, which helps a lot with pointers and aliasing and ensuring that that is not something that can happen. We do not require any manual tuning, and we also do not require any scopes. So we just look at the entire program and optimize it accordingly. To take one example, for the MVT benchmark, we observe here that data is updated and we are able to parallelize this benchmark. We are the only benchmark, the only compiler that is able to correctly identify this pattern. This is not the only case. There are other examples for which we are the only ones to expose the parallelism and improve performance significantly. There are other instances, however, where because of the lack of polyhedral analysis, we are not able to find the parallelism, whereas Pluto and Poly do. And finally, there is also some work left to be done for LU, there is an auto-parallelization opportunity missed, which we will improve by making the detection of parallel patterns more powerful. As an overview, in our approach often finds parallelization where others cannot. And even if we do not find such opportunities, we are never slower than the state-of-the-art compilers today. We did not we were not satisfied with just small polybench kernels. We wanted to test our approach on a larger code. For this, we have used the exascale proxy app from LNL, Lulesh, which is an unstructured hydrodynamic solver. So they have issues, an issue here in the optimization and compilation procedure is the fact that there are indirect accesses. So to know which elements are accessed, another array of these indices are called. And analyzed. There are multiple versions of the Lulesh code, and the developers provide a manually tuned OpenMP implementation. However, as a base of our approach, we only use the serial version provided, not the parallel OpenMP implementation. So, for example, this is the serial result accumulation, and this on the other side we see the parallel result accumulation. Surprisingly, not only were we able to outperform the other parallelizing compilers, we are even able to outperform the version of this program manually tuned by the developers themselves. Because we do not rely on a more complex reduction scheme, but rather just on parallelizing the serial version, we are able to outperform the parallel version of Lulesh by up to 20%. In conclusion, I would like to say that it is possible to lift C semantics from C into the SDFGIR and then create optimized and improved programs by use of Dataflow analysis. However, symbolic analysis is needed to understand data movement. Another key lesson is that update detection opens new parallelization opportunities. Access pattern propagation allows for efficient whole program analysis. And as a conclusion to my entire talk, understanding data movement is key to performance and portability. Thank you for listening to my talk. I would like to also add that the paper is available, and both the code prototype for C2 days and days itself, everything is available on GitHub freely. Thank you very much, and I wish you a good day.